and actually it's kind of going to be a completely different talk. The point of view is totally different, but of course it's still featuring this Heisenberg category. So let's just quickly remind you where we were. So unlike last week where I was working over the complex numbers because I was doing the K0 calculation, which is only true in characteristic 0 and depends on things like the group algebra of the symmetric group and so on. Today I'm going to work over any algebraically closed field K, and we're going to be studying module categories over the Heisenberg category Heis K. So the little k there, that's the central charge, which is any integer. And I'm going to tell you the story for the Heisenberg category that we had last week, which is the degenerate Heisenberg category. But it's worth pointing out there's also a quantum version of the Heisenberg category, which is a little bit more complicated to define. And everything in the theory that I'm telling you today, it's totally uniform in the two cases. And many of the module categories that you're interested in representation theory need that quantum version of the Heisenberg category instead. But the degenerate one's a bit easier. So that's all I'm going to talk about. So let's just really quickly remember the definition. So that's a strict K-linear monoidal category. It's got just two generating objects up and down, and then these four generating morphisms that we had last time. And I've just written out the relations quickly again here, which should look kind of fairly familiar. The first three relations are from the degenerate affine Hecke algebra. Then the down arrow is a right dual of the up arrow. And then this most difficult relation, which is saying that this matrix, which matrix depends whether the central charge K is negative or positive, this matrix has to have a two-sided inverse. So for example, in the case that the central charge K is less than or equal to 0, this is a 1 by K plus 1 matrix. So it defines a morphism here from up down direct sum some copies of 1 to down up. And I'm just basically forcing that those objects are isomorphic by this relation. So that's this Heisenberg category that we're studying. So this category, it acts naturally on a whole bunch of important Abelian categories that I'm sure you're all very familiar with, kind of classical categories we've been studying for 50 years or 100 years in representation theory. And to me, the whole point of this Heisenberg category is it kind of provides this totally uniform language to discuss all of these important categories in representation theory simultaneously from this new point of view. So we're going to always be interested in some Abelian category that will be called C. I'll give you some examples in a minute. That's what we're always going to be studying in this general theory. So it needs to be a module category over the Heisenberg category Heis K for some central charge K. That just means that there's some monoidal functor from this Heisenberg category to the monoidal category of endofunctors and natural transformations of C. Okay, so each of the objects of C, that's going to act, each of the objects of the Heisenberg category is going to act as some endofunctor of the category C, and the morphisms in the Heisenberg category are going to define natural transformations between those endofunctors. And I need some finiteness. The finiteness condition I want to put on C today is just that it's a locally finite Abelian category. So that means that all objects in this Abelian category C have finite length, and all the morphism spaces between two different objects are finite dimensional. Okay, so that's kind of essential because we're going to be doing things like looking at Jordan blocks and eigenvalues and such like. So we want finite dimensional morphism spaces. So let's just give a few examples to kind of convince you that this includes lots of categories that you like. We talked last week, in fact, that was the motivation for defining this Heisenberg category last week. When the central charge is -1, the Heisenberg category acts on modules over the symmetric category sim. You remember in my language, this symmetric category, that was, well, the path algebra of the symmetric category is just the direct sum of all the group algebras of all the symmetric groups, and that shouldn't be a C because we're working over any field. This is really interesting now when the field is of positive characteristic, when this abelian category has got interesting structure. So in that example from last week, the up arrow in Heisenberg was just acting as this usual induction functor from Sn to Sn plus 1, and the down arrow was the restriction functor. Next example, generalizing that first example, any negative central charge, Hei's minus k, it acts on modules over these algebras Hn upper F, which are the cyclotomic Hecke algebras. So these are the quotients of the degenerate affine Hecke algebra, where you impose some polynomial relation on the first Eusis-Murphy element. And if that polynomial is monic of degree k, this gives you an action of the central charge minus k Heisenberg category on that. So again, the up arrow is acting as some natural induction functor, and the down arrow is the adjoint restriction functor in that example. For me, the example I like the most actually is central charge 0. So this is Hei's 0. And my favorite category of all time is the category of rational representations of the algebraic group GLN over a field of positive characteristic P. So Hei's 0 acts on rep GLN. So now the up arrow acts as tensoring with the natural GLN module V, and the down arrow acts as tensoring with the dual natural representation. The only relation you have to really check is that the sideways crossing, remember that matrix that had to be invertible in central charge 0, that's just a 1-by-1 matrix. It's just saying that that rightward crossing has to be an invertible morphism. And in this case, the rightward crossing is just going from V tensor V star tensor blank to V star tensor V tensor blank, and you just calculate what that morphism is. It's just the obvious tensor flip, which is of course invertible. That's how on the surface this Heisenberg action is in central charge 0. I didn't write it down, but the dot morphism in this case, that acts as the Casimir tensor. So it's kind of something rather natural that you have sitting there. So this third example, although that Heisenberg 0 category looks rather boring because we haven't really inverted anything interesting, we've just inverted this rightward crossing, so that relation is sort of a trivial relation. There's a ton of examples along these lines involving the general linear group, or the general linear Lie algebra, or the general linear Lie superalgebra, or if you go to the quantum Heisenberg category, then you get quantum GLM, perhaps at a root of unity, or maybe some restricted enveloping algebra. There's just basically any kind of type A-ish classical category in representation theory. This Heisenberg category acts. And usually that action is just on the surface. It's just a sort of a trivial thing to construct. The relations are usually very easy to see. Anyway, so we've now fixed our locally finite abelian module category C, and I want to try and show you this sort of general machinery for studying all of these abelian categories in a uniform way from this Heisenberg point of view. So the right way to work with this Heisenberg category is to work with generating functions. So I'm going to try and teach you a little bit of how to do that. Really, I think working with these sorts of category like the Heisenberg category or categorified quantum groups and a bunch of other examples, you know, it's similar to how you should work with things like symmetric functions or Yangians or quantum affine algebras. You should really use kind of just generating function techniques. So let's just try and set that up so that you see how it goes. So to start with, I've got the rightward crossing, which I already defined earlier, but I need to introduce the leftward crossing. And I had the rightward cups and caps, which were generating morphisms, but I need to define the leftward cup and the leftward cap. So that's kind of just a little bit of silly chasing of definitions of this presentation of Heisenberg that we started with. The leftward crossing is just, remember that matrix that had to be invertible? The leftward crossing is just the first entry of that inverse matrix. And to define the leftward cup and cap, it depends on whether your central charge is positive or negative. If your central charge is negative, then that leftward cap turns out just to be the last entry of that inverse matrix. But if k is greater than or equal to 0, that leftward cap gets defined as this strange curl with k dots on it. So it's not too important to know that definition. It's just you introduce this leftward cup and leftward cap. And the important point is that this gives a strictly pivotal structure on this Heisenberg category, so that these diagrams become very natural to use and work with up to an isotopy. So once we've got them, now let's get to generating functions. So the notation I use when I want to put n dots on a string, I label that single dot by the monomial x to the n. And then I can start labeling dots by polynomials in x. Right? Polynomial being a linear combination of monomials. So you just take the corresponding linear combination of these dots with multiplicities. Okay, so I'm going to always label dots with polynomials in x. And then I use this variable u as an indeterminate. And when I work with generating functions, everything I write down is going to be a formal Laurent series in u inverse. That's kind of a weird convention, but I think that's standard in, for example, Yangians. That's how you set up these generating functions. So just to warm you up into using generating functions, here's a dot labeled by the formal power series u minus x inverse. So you should think of that expression 1 over u minus x. You should expand it in terms of u inverse, that to interpret that. U is just this formal variable in our generating function. So when you do that, it's just the identity morphism on the up strand, that's the u inverse coefficient. A single dot is the u to the minus 2 coefficient, 2 dots is the u to the minus 3 coefficient, and so on, right? So this one single gadget, that's kind of the generating function for all numbers of dots on that string, depending on which power of u you're looking at. Okay, so that's the most basic generating function. And the following is a total triviality, but I mean, maybe you remember it from I don't know, maybe when you did complex analysis or something and you were taking residues, you remember this sort of trick. This is a trivial trick. Let's just make sure that we've all got it in place. If my polynomial f of x is just x to the n, what have I got on the right-hand side? F of u is u to the n. And by this notation here, I mean take the u inverse coefficient of that formal Laurent series. So how do we get a u inverse coefficient here? Well, from this term here, we need to be taking u to the minus n minus 1, if f of u is u to the n. And u to the minus n minus 1 comes with a dot with n dots on it, dot to the x to the n. So I just proved that trivial basic trick with formal power series that I think you all know, but so that's checked it for a monomial, so it's true for any polynomial. So I'm going to manipulate formal power series a little bit in a minute, and I just want to make sure that when I use that basic trick to move a polynomial labeling dots from one strand to another, you realize that's all that's going on. It's that kind of trivial but very useful trick. Okay, so I'm trying to build this calculus of this Heisenberg category a little bit. Bubbles, these dotted bubbles, they're very important in this theory. They're just elements of the center of the Heisenberg category, endomorphisms of the unit object. So when you're acting on this Abelian category C, these dotted bubbles define elements of the center of the Abelian category C. The center just means endomorphisms of the identity functor on C. So if you want to understand things like central characters of this Abelian module category C that you're acting on, you need to really understand these dotted bubbles. So this calculus of bubbles, that's really the calculus of central characters for this Abelian category C that we're acting on. So I'm just, you know, I'm happily spending another 10 or so minutes kind of training you up in these generating function techniques, because really the same tools you use in all of these diagrammatic categories, and I think it's an important technique to see. So what I want to do is I want to put these dotted bubbles together into a generating function as well. So this is the counterclockwise bubble generating function, right? Bubble of u. And this means put all the counterclockwise bubbles with any number of dots. So that dot is labeled x to the n in there, and that's just sticking it in a generating function. So the bubble with n dots, that's the coefficient of u to the minus n minus 1. And similarly, there's this clockwise bubble generating function, where it's the clockwise bubble with n dots that's the coefficient of u to the minus n minus 1. So this is a kind of confusing place. I think Aaron Lauder first had this idea with categorified quantum groups. If you've never seen it, it's a bit confusing. So this is simultaneously a definition and a theorem. You see, dots only make sense with a non-negative number of, but you can only label dots by a non-negative number, by x to the n, a positive monomial in x. And depending on the sign of k, of the central charge, one of these expressions involves dots with some, it involves bubbles with some negative number of dots. So finitely many of the terms that I've written down are undefined at this point. One of them always makes natural sense, always, depending on whether k is positive or negative. But either the counterclockwise or the clockwise one has some undefined negatively dotted bubbles in, which Aaron calls fake bubbles. But the thing is, this relation holds. This counterclockwise generating function times the clockwise generating function, when you multiply them, that's 1. And so using that, you can work out what the finitely many fake bubbles have to be in terms of other bubbles. And then the theorem says that once you make the unique choice you have to, then this infinite Grassmannian relation holds. So probably most of you are totally familiar with this trick if you've seen this diagrammatic calculus, so this is not a big deal. So that gives us these generating functions for dotted bubbles. They're super important because that's going to be our calculus of central characters of our category C that we're acting on. And that same basic trick, that trivial fact about power series that I told you on the previous slide, for these dotted bubbles, that says if you have a bubble labeled by f of x dots, you can calculate that by taking this generating function, bubble of u, times f of u, and then calculating the u inverse coefficient of that expression. Okay, so that's just a trick for manipulating these generating functions. So now I've got generating functions, I can now start to write down some of the more important relations in this Heisenberg category. These were not my defining relations, but you just calculate, and these are consequences of the defining relations in the Heisenberg category. So the first one tells you how to expand a curl labeled by some polynomial number of dots. Okay, so this is a curl with f of x dots on the curl, and it says, well, you just take this expression, f of u in our indeterminate, that was the generating function for dots on the down strand, and that's the generating function for dotted bubbles. You calculate that and you pull out the u inverse coefficient. So that to me is the right way of writing this curl relation. It's very slick. I'm going to just do just enough in a bit to convince you how important that relation is. But you can only see that once you start using these generating functions.
May I ask a quick question?
Yes.
When you draw your bubble, you assume that there is nothing inside it, or anything could be put inside?
That is correct. I mean, really, I should shrink this bubble down to a tiny dot, right? It's a sort of infinitesimal bubble concentrated at that tiny dot. It's just a weird diagrammatic notation, which I think is suggestive. But you should think of it as concentrated at the origin of the bubble with nothing inside. I need to look at my comments. Okay, I'm not able to answer that question, but that's a sort of more advanced direction that I think this Heisenberg category should be taken, but it hasn't really become so developed yet. Let me write down one more relation, which is the bubble slide relation. So here I'm trying to take my dotted bubbles. So I'm using this generating function, which is all of them, and you need to know how to pull it past the strand. And the relation says that the bubble slides to the right-hand side of the strand, but it creates some dots on that strand when it does so. And the number of dots, well, it's this rational function, u minus x inverse, over u minus x minus 1 and u minus x plus 1. And of course, you have to expand that as a formal Laurent series in u inverse. And when you equate coefficients, that records all of the bubble slide relations in one single formula.
John?
Yes.
Nito is asking, can I see this as a verification of the VOA?
Yes, I saw that, and I tried to mutter something about it. I don't have a good answer to that question.
Thank you.
Mm-hmm. So look at that rational function. That'll show up in a little bit. The zeros and poles of that rational function are important, and you'll recognize them shortly. But maybe those two relations, just seeing those relations written using generating functions, if you've seen these sorts of curl relations or bubble slide relations written out without generating functions, they're rather painful and look rather mysterious. I find once you put them into generating functions, you suddenly understand what's going on with these weird relations. So I'm going to try and illustrate that just in the first part of the talk. So I'm gonna actually prove the following lemma. So this lemma is due to Ben Webster, and I think it's a totally fundamental fact about this Heisenberg category, and there's an analogous result for categorified quantum groups as well. So let's take an irreducible object L in our abelian module category C. And so this dot on the upward strand, that defines a natural transformation from the up functor applied to L to itself. So I'm going to define M sub L of X to be the minimal polynomial of that natural of that endomorphism. Okay. So ML of X, it's the minimal polynomial of the up dot acting on the object L. And similarly, N sub L of X is going to be the minimal polynomial of the down dot acting on L. Okay, so we're in all our morphism spaces of finite dimension. That makes sense. And these polynomials ML of X and NL of X somehow capture crucial information about the irreducible module L. So now I'm going to be interested in this dotted bubble, this counterclockwise dotted bubble generating function. Of course, things in the center of the category, they act on irreducibles as scalars by Scher's lemma. So when you take this dotted bubble generating function and you evaluate it in L, you get a formal Laurent series with coefficients that are just scalars in our field. Because of the definition of the dotted bubble, this formal Laurent series, its top term is u to the k, and then it's got lower terms because we're doing power series in u inverse here. So this dotted bubble evaluated on L, that's sort of encoding all of the central character information about that irreducible module L. So that's going to be very important, that formal Laurent series. I'm just going to call it OL of U. Okay, so O, that's meant to remind you of that bubble. OL of U, it's that counterclockwise bubble evaluated on L. I'm just looking at the questions. Is there a good explanation for
okay,
the...
So for the sake of the recording, I'm going to read out the question to you.
Yeah.
Is there a good explanation? Oh, Katerina asks, is there a good explanation for the asymmetry in the two curls? One has a relation and the other doesn't. I do understand the outcome, but would like to know how one would come
So I don't think there's any asymmetry. I think maybe you're thinking of Michael's original Heisenberg category where he has asymmetry. But once you go to this Heisenberg K with central charge K, you realize that the two curls are just the same. In fact, when you write the curl relations in terms of generating functions with dots on, they become the same. Does that answer your question enough? So there's no asymmetry here. It's just maybe Michael was just showing you a glimpse of a special case. Okay, so what's the lemma? This formal Laurent series, the central character information in this OL of U, it's equal to the rational function NL of U divided by ML of U. So somehow all that central character information you can get by taking the ratio of these two minimal polynomials. So that may not look important, but this to me is the heart of everything in this game. So one consequence of that, of course, because this OL of U, its leading term is U to the K, that means this rational function must have leading term u to the k when you expand it as a formal Laurent series. So the degrees of these minimal polynomials, the difference in the degrees is the central charge. So I'm going to try and prove that lemma in about 5 minutes, because I think it's super important, and it's the place you really see this generating function technique just all coming together. So we're going to try and prove it. I know it's a bit of an effort to follow a proof. So here's the proof. I'm going to define f of u to be the minimal polynomial for the dot on the upstring times this OL of u. So that's a formal Laurent series in U inverse with, in fact, it's not just a formal Laurent series, it's actually a polynomial in the variable u. So to see that, all I have to convince you of is that the u to the minus n minus 1 coefficient of that formal Laurent series is 0 for all n greater than or equal to 0. And to calculate that u to the n minus 1 coefficient, all we've got to do is calculate the u inverse coefficient of this expression. That's f, right, in there. So I've got to convince you that this is 0 to prove that's a polynomial. But by the basic trick, this is just the counterclockwise bubble labeled by x to the n, ml of x dots. ml of x, that's the minimal polynomial for that dot on the upstrand. So that acts as 0 on L, because that's the minimal polynomial for that endomorphism. Yep, that proves that's a polynomial. Okay, so I used my basic trick. So now we know that f is a polynomial. It now makes sense to look at a downstrand labeled by f of x dots. It wouldn't have made sense until we knew that that f was a polynomial. Well, by our basic trick, the downstrand labeled by f of x dots, that's this expression. And now I'm just expanding the definition of f of u. F of u is ml of u times bubble of u. So this next one is just the definition. But now that curl relation kicks in. What we've got here is exactly the curl relation. So this is equal to this curl with ml of x dots sitting on that curl. But now we've got minimal polynomial number of dots on that upward strand acting on L, so that's 0. Okay, so
can you remind us, so L is a simple object.
L is always a simple object in our Abelian category C.
The module category over the Heisenberg.
Correct.
In this version of the Heisenberg, you keep track of the weight of the regions. You keep track.
No, I don't. No.
So you just take monoidal category.
What I mean here, I'm kind of, I'm using this sort of calculus for module categories as well. When you're acting on a module category, you can just put a module on the right-hand side of your diagram. Does that make sense?
Yeah, right. And but you take any module category over Heisenberg and any simple object, or you need some condition?
The only condition I need is this: that my category is locally finite Abelian.
Sorry, what's the condition?
I need it to be a locally finite Abelian category.
Yeah. I see. So every object has finite
length, and every morphism space is finite dimensional. Since my field's algebraically closed, that implies in particular that the Schur's lemma holds. The simple objects have just K as their endomorphism ring.
So the conditions that the home space is a finite dimensional, or thank you.
Yes. Okay. So yeah, you definitely need some finiteness because I'm talking about minimal polynomials and central characters. And okay, so what have I just proved? I've just proved that this expression, if you put f of x dots on the downstrand, it's 0. But remember, nl of x, that was the minimal polynomial for dots on the downstrand. So that shows that nl of x divides the polynomial f of x. In particular, the degree of the polynomial nl of x is less than or equal to the degree of f of x, which by definition is the degree of m plus k from here. And now you do the same argument, but with all the orientations reversed. Exactly the same argument, you get this inequality in the other direction. The degree of m is less than or equal to the degree of n minus k. And those inequalities both mesh together. So in fact, equality holds in both places. And so that proves that the degree of f of x equals the degree of n. And since we already had n dividing f, it follows that they're equal. And so in fact, I proved that this guy is exactly n, and that proves the lemma. It was a bit of a struggle, but I exactly proved that this guy is n over m. And so it's such an unbelievably slick proof, and it really shows how this curl relation is crucial, that I think it was worth that effort of seeing these generating functions. If you try and write this out without generating functions, it's just a total nightmare. So it convinces
So if you flip between from k to minus k, do you exchange n and m?
So remember, I've got this counterclockwise dotted bubble and this clockwise dotted bubble. The counterclockwise one has leading term u to the k, and the clockwise one has leading term u to the minus k. So when I repeated that argument, I reversed all orientations. So that was with the clockwise bubble.
If you were to use the symmetry with sense k to minus k, you would flip numerator and denominator.
Yeah.
Of your function.
Mm-hmm. So that's where this second guy comes from. It's just the same argument, but you flip. So this minus k is because it's the clockwise bubble, not the counterclockwise one. Okay, so that was a proof. Now so this Webster's lemma I really think is really crucial, and I'll hopefully convince you of the importance of these rational functions, these OL of U's. I mean, it's really we're dealing with the combinatorics of central characters for all Abelian module categories over Heisenberg at once. To me, it's amazing that you can unify all of these classical categories with the same point of view. Okay, so let's carry on. Let's develop a bit more theory. So there's our category C. So the next thing I've got to define the spectrum of C, which I call capital I. That's just going to be a subset of the field. And the spectrum, it just means the set of eigenvalues of all of these up dots acting on all irreducibles L in C. Okay. So in other words, the elements of the set I, they are the roots of all of these minimal polynomials ML of x. Right? ML of x is going to factor as the product over I, linear factor x minus I to some power, and I denote that power, the multiplicity of I as a root of that minimal polynomial, I denote that by epsilon I of L. Right? So L is always an irreducible module in our Abelian category. Okay, so that's all I is. It's just where the roots of these minimal polynomials live. And you can show that this other minimal polynomial, the minimal polynomial for the dot on the down strand, NL of x, that also has exactly the same set of roots, this same spectrum. So NL factors into linear factors, and the multiplicity of I as a root there, I call phi I of L. So this defines in particular some numbers epsilon I and phi I for each irreducible and each I in the spectrum. So these are going to turn out to be these Kashiwara epsilons and phis in the theory of crystals, but this is where they come from for us. So now I've got this endofunctor defined by the up arrow. It's an endofunctor of the category C, and down arrow is an endofunctor of the category C. And these dots give me endomorphisms of these endofunctors. So I'm going to just decompose them into generalized eigenspaces with respect to these dot endomorphisms. Okay, so I'm going to call that E sub I. That's going to be the generalized I eigenspace of the up dot acting on that functor. Okay, so EI, it's a summand of that endofunctor of C. And when pictures, I don't write EI in pictures, I just label the up strand by the color I being an element of the spectrum. And similarly, Fi, that's the generalized I eigenspace of the down dot, acting on the down arrow endofunctor. I call that Fi, and in pictures, I just label the down strand by the color I. Okay, so I've decomposed these endofunctors up arrow and down arrow into EIs and FIs by these eigenvalues, and I is in this spectrum. So you have to do a little bit of work here. You have to show that this spectrum actually is closed under this map's adding 1 or subtracting 1. So my spectrum is closed under this. And then I'm going to look at the quiver, which has this set I as its vertices, and it has an edge from I to I plus 1 always. Okay, so this gives us a quiver where all the components of this quiver, well, it depends on what characteristic you're in. If you're in characteristic 0, this is just the components of this quiver is just A infinity components. Or if you're in characteristic P, then the components are all these cyclic quivers, AP minus 1 up 1. And I'm going to let G be that Cax-Moody Lie algebra associated to that quiver. Okay, so that comes from this spectrum of your category C. So that somehow that spectrum is some sort of discrete thing. So this Cax-Moody depends on the spectrum. And then I'm just going to use usual Lie theory notation. So X will be the root lattice of that Cax-Moody, alpha i's will be the simple roots, and so on. Okay, so I'm not going to write all that down. So now back to our irreducible L in our module category C. I'm going to define the weight of L now. So this is going to be a linear combination of the fundamental weights for this root system. And the coefficient of the ith fundamental weight comes from these phis and epsilons, phi of L minus epsilon I of L. Remember, phi was the multiplicity of I as a root of n of x, and epsilon was the multiplicity of I as a root of the minimal polynomial m of x. And then there's this difference, this is the coefficient of lambda I. In other words, that coefficient, it's the multiplicity of I as a 0 or a pole of that rational function, that OL of U that I had, because that was the NL divided by the ML. Okay, so this encodes all the numbers that are those multiplicities of zeros and poles in all those rational functions, encoding all that central character information of all those bubbles. So here's the theorem. I'm going to define, so for a weight lambda of this Lie algebra, define C sub lambda to be the Serre subcategory of C generated by all the irreducibles of weight lambda, where this is the definition of weight. Then the category C decomposes into blocks as the direct sum of all these C lambdas. Moreover, the functor EI sends the subcategory C lambda into C lambda plus alpha I, and Fi sends C lambda into C lambda minus alpha I. Okay, so you're starting to see Cax-Moody action and understand the notation here. I see some questions. Hang on, I'm just.
We have a question from Victor. Yeah, Victor, is it not true that psi and epsilon is 0 or 1 for irreducible L? And
that is. So let me answer Victor's question. That's definitely not true. These dots. I mean, if your category is semi-simple, that's true. But if our Abelian module category is not semi-simple, you get big Jordan blocks for these dots acting on these things.
And so I just wanted to also ask, so in the weight of WT of L formula, the coefficients of lambda I are integers. Phi I minus epsilon I.
Yes, because these phis and epsilons, they were multiplicities of roots of these minimal polynomials. Okay, so is that all okay? In fact, if you look at the Grothendieck group of the category C and you complexify, we've got this decomposition of C into blocks. Of course, the Grothendieck group decomposes correspondingly into blocks. They give the weight spaces, and these EIs and FIs, when you pass to the Grothendieck group, they give you an action of the Lie algebra G on that complexified Grothendieck group. And these are exactly the weight spaces, just as the notation suggests. So it's a little bit remarkable that you start with the Heisenberg action and you actually end up with this Grothendieck group being a module over the Cax-Moody Lie algebra G here. But maybe it's not that remarkable. You see, the Heisenberg gave you these up arrows, but because you can decompose into eigenspaces, you can actually refine these functors to get these Cax-Moody endofunctors, these EIs and FIs acting. So somehow in categorification, this Heisenberg action actually upgrades to a whole Cax-Moody action. Kind of, it's sort of hidden in there. Okay, I'm not going to try to prove this, but I wanted just to convince you of these bubble slides and explain where they came from. So remember that the multiplicity of lambda I in weight of L That's the multiplicity of I as a zero or pole of this bubble of U rational function that we have by Webster's lemma. And now what we want to do is we want to understand, what I'm trying to explain is this part of the proof, why EI sends C lambda and C lambda plus alpha I. So what we've got to do is we've got to take an L whose weight we know, we've got to act with the functor EI and understand its central character. So we've got to understand how this bubble series acts on EI of L. Right, so that's taking the bubble, it's applying EI, which is this colored up strand, this summand of the up arrow to L. And so what I've got to do is I've got to slide that bubble over there before I can work out stuff about its central character. So I use the bubble slides, which tells me that it slides over at the price of this rational function. Now, if we're just looking on eigenvectors, we can replace the x here just by I, because we've taken the generalized eigenspace of eigenvalue I for these dots. If you replace those x's by i's, you get this expression. So this shows that if you've got an irreducible constituent L prime of EIL, its central character information in its O of U series is the one for L multiplied by this rational function. And so you see what's going on. When you multiply by this, you're adding 2 to the multiplicity of I as a 0, and you're subtracting 1 from the multiplicity of I minus 1 as a 0, and you're subtracting 1 from the multiplicity of I plus 1. So what's going on is this definition of the weight for L prime is the weight of L. We've added 2 i's, and we've taken away an I minus 1 and an I plus 1, and of course that's the simple root alpha I. This is this crazy rational function in the bubble slide, and now you see it's just encoding the Cartan matrix of type A, which is hiding in this Heisenberg action. Okay. So let's sort of so now we've kind of got this Kac-Moody action, and we're kind of plugging into a big existing theory which has been developing for 20, 30 years or so. Let me write down another theorem along the same line. So let B be the set of isomorphism classes of irreducible objects L in our Abelian module category C. And then the theorem says that set B is actually a perfect basis for the Grothendieck group of C. So I'm not going to write down this definition. The idea of perfect basis was introduced by Berenstein and Khovanov quite a while ago. In particular, this set B has the structure of a crystal in the sense of Kashiwara. And you need these Kashiwara operators, EI tilde and FI tilde. EI tilde on L, well, you act with the functor EI, and then you take the Sokal, which turns out to be irreducible. That's how the Kashiwara operator acts if that's not 0, or else it's just your empty symbol otherwise. Similarly, Fi. So EI tilde and Fi tilde come from looking at looking at Sokals of these functors EI and Fi applied to L. These epsilon I and phi parts in Kashiwara's notation for crystals, those are those multiplicities of I as a root of the minimal polynomials M and N that we had. And the weight function, well, I defined that. In fact, it's totally, in this total generality, the endomorphism algebra of EIL is always just a truncated polynomial algebra, and these epsilon i's are just what you're truncating by there. And similarly for these f's. So this theorem is, I think it really started with Granovsky and Vazirani in like 1998, 99, and then Chuang and Ruquier kind of axiomatized it a little bit. But to me, this Heisenberg setting is really the perfect setting for a lot of this setup. Maybe I won't really mention this example very quickly, but for these cyclotomic Hecke algebras that I had, these categorify irreducible lowest weight modules. And so in that case, it's just kind of automatic by uniqueness of crystals coming from perfect bases, that this crystal B in that case is just this Kashiwara crystal for this irreducible lowest weight module. Okay, so one more theorem just to show you here. which is, so somehow that previous theorem was sort of building on 30 years of work. I wouldn't call it really new. It's just in a new language. This Heisenberg language is perfect for that, for this stuff. But this theorem I'm very proud of. And let me just tell you, so let's fix a weight lambda. So that's fixing a block of this category C that we're acting on. And let's just assume that hi lambda is less than or equal to 0. There's a similar story when it's positive, but I'm not writing that down. And then I'm looking at this block C lambda of the category defined by the weight lambda. So this row vector of natural transformations defines a natural transformation from EI Fi, direct sum the identity on this block, to Fi EI on this block. And the theorem says that this crazy row vector of natural transformation, so this first one is a little bit weird. This is this rightward crossing in Heisenberg, but I've restricted to the summand EI Fi there. And then I've got this rightward crossing, which is the actual rightward crossing in the Heisenberg category in that. So that notation's a bit weird. I'm going to just skip over it. This natural transformation is actually an isomorphism. And there's a similar theorem when this inner product is positive. And the proof is kind of remarkable. I spent years trying to prove this result. And it wasn't until I started working with Ben and Alistair that we suddenly had faith in just proving it naively using the Chinese remainder theorem. And I'm going to try and convince you that this is a very important theorem. If you combine this theorem with an existing isomorphism theorem between these degenerate affine Hecke algebras and quiver Hecke algebras, these KLR algebras, you get right away that this category C that we started with this block decomposition, in a canonical way, you can turn this Heisenberg categorical action into an action of the categorified quantum group, the Kac-Moody-2 category of Khovanov, Lauder-Ruquier. So I call that U of G. This Heisenberg action automatically gives you an action of this categorified quantum group in the sense of KLR. And conversely, if you start with a suitable 2 representation of the Kac-Moody-2 category, you can reverse this construction and construct a Heisenberg action. There's some technical hypotheses because this central charge K has to be fixed and so on. And I could state this corollary in more fancy language. Really, there's a category of module categories over Heisenberg, and there's a category of 2 representations over the Kac-Moody-2 category. Really, these are equivalent categories. That's really what's going on in this construction. You can go back and forth. So as I said before, somehow this Heisenberg action, it already sees everything for a Kac-Moody action. That's what's going on here. And this theorem is the absolute key to proving that. It somehow upgrades this isomorphism theorem between affine and quiver Hecke algebras. It somehow upgrades it to this monoidal category setting of Heisenberg and the Kac-Moody-2 category. It really tells you how to kind of add in these cups and caps into this isomorphism, this kind of weird, difficult inversion relation of this matrix being invertible. That's what transfers that to the analogous relation for Kac-Moody-2 categories. So this is very, very nice because it says as soon as you have...
Sorry, Chio has a question in the chat. He's asking the Heisenberg category.
You know...
Well, let's just read it. So does the Heisenberg category inherit the grading from KLR2 category via this theorem?
Not really. I mean, what I think you could show is that you could take some completion of the Heisenberg category, and that would be isomorphic to some completion of the Kac-Moody-2 category. And then, of course, they would be the same, but only after this completion. And it's not a natural thing to complete the Heisenberg category. So I kind of feel that if you want the grading, you should go to the Kac-Moody-2 category, and that says it nicely. Is that the U is the log of Q in KLR. I don't know what that means, that question. No. You're going to have to pass on that one. This machinery lets you say that if you have a Heisenberg action, you get a Kac-Moody action, and it's kind of, it's a totally natural way to get that action. This theorem makes that totally natural. Before this, we had to prove this using a result of Rouquier, which Rouquier called control by K0, which I think is a sort of a much harder and a more sophisticated result. And it was this way, it's sort of just saying, look, Heisenberg action is actually where you should start. And there's lots of kind of reasons these Heisenberg actions are more natural. It's on the surface in all these examples in representation theory. And somehow you can deform all of those examples and the Heisenberg is totally adapted to deformation, whereas this Kac-Moody is a very rigid thing. Somehow it's this passage to this spectrum that I had earlier, which is that this is the spectrum which is sensitive to deformation and changes kind of discretely. So I was going to just mutter something very quickly at the end with an example. My favorite example is rational representations of GLN. So there's the Heisenberg high zero acts. So the spectrum is just generated by one. In this case, you can identify what the Grothendieck group is. It's a module for the Lie algebra SLP hat because of what the spectrum is. It's just kind of the natural representation of SLP hat, a natural level zero representation. And then the Grothendieck group of rep GLN is the nth exterior power of that natural representation. So I'm just being very quick because I don't want to say a whole lot. Let me see. So the classes of the, that shouldn't be L, that should be of the, this should be the standard modules. That this is a highest weight category. The classes of the standard modules go to the monomial basis of that wedge product. The class of the trivial module that goes to this vector in that, and in this action, actually the trivial module it generates the category of tilting modules for GLN, sitting inside of rational representations of GLN. And so you deduce from this that this category of tilting modules for GLN, by this theory, it becomes a cyclic 2 representation of this Kac-Moody 2 category. And maybe I'll just write this last theorem down. In fact, you can providing P is bigger than the Coxeter number, you can exactly identify the category of tilting modules for GLN. Since it's a cyclic 2 representation, you ought to be able to give it a presentation. So I've written down here a complete set of generators and relations for tilt GLN as a cyclic 2 representation of the Kac-Moody 2 category. It's not very important to read that. It's interesting because this is a homogeneous ideal in the Kac-Moody 2 category. So this presentation for tilt GLN coming from Kac-Moody 2 category gives you a grading on the category of tilting modules. Of course, much more known, and I think that's a good place to stop right there.
Well, let's thank John. So we'll have questions. So let me ask a question. So in the tilt GLN, if you pass to the Grothendieck group, what module do you get?
So, I mean, it's the same module. I mean, you're just getting different bases for that same module.
So it's this module over.
This is a module over the integers because it's a highest weight category, right? For a highest weight category, you can take the standards or the tiltings or the irreducibles. They all give they just give different bases for the Grothendieck group. It doesn't depend in highest weight categories.
And you have it. You have verification with grading with Q or verification without grading in this case. So
you get tilt GLN, this Cherubian monoidal category. That's exactly the quotient of the Kac-Moody 2 category that you get the presentation for.
So it's with the Q. So you still have grading. Sorry.
So from this presentation for tilt GLN, you get this grading on tilt GLN.
And it's a new grading.
No, I think I'm quite sure it's the same as a grading which was constructed by Risch and Williamson, but they construct it using Zergel bimodules, and in fact they only do the regular block.
So it was still tricky to construct. It's a tricky. It's not immediate.
It's not immediate, no. Yeah, but somehow this approach is quite clean and gives you this grading on all blocks, kind of quite naturally. So I thought I would mention it.
Katharina is asking, can you read for me again the home in the formula in the last theorem?
Yeah. So in this Cax-Moody 2 category, you have these kind of various kind of universal 2 representations where you just fix the weight at the right-hand edge of your diagram. So that's what this is. This is this universal cyclic 2 representation where I fix that particular weight.
So it only depends on, it depends on n only.
This involves n.
Yeah, okay.
And then it's the quotient of that universal one by these relations. So this first relation, this you would impose if you were getting the usual generalized cyclotomic quotient that categorifies the lowest tensor highest weight representation of that weight. And then there's one extra relation here that you need to get tilt GLN from that, which is a slightly weird relation where this again has n in it, right? And look, here there's a p.
So do you get anything reasonable if you leave out the last relation?
So if you leave out this last relation, then this is this generalized cyclotomic quotient.
On the nose, okay.
Which categorifies this lowest tensor highest weight representation.
Does the Grothendieck group change if you add this relation? If you add the second relation, does the Grothendieck group change?
No, the quantum groups, I mean, that's, so there's a larger category than tilt GLN, which is this Deligne category.
But which Deligne category?
Wait.
Oh, sorry, I guess I lost the connection.
So I mean, so this okay. So how do I mean, maybe this only really makes sense in characteristic 0. And in characteristic 0, tilt GLN is semi-simple, and it's the semi-simplification of the Deligne category, rep GLN. And in characteristic P, there's still an analog of that. There's still this larger category, which is sort of diagrammatic in nature. And tilt GLN is a quotient of that larger category, that's what you get if you drop that last relation, in fact.
So for the Deligne category, you mean the oriented?
The oriented Brouwer. So the Karoubi envelope of oriented Brouwer. And if you can take that exact category in characteristic P. Maybe I was gonna, I mean, I was gonna say a little bit about that, but I ran out of time, so that's good.
Great, thank you. Some more questions?
I have a question, John. Can you use the cellular structure of the Heisenberg category to transfer it to some sort of cellular structure on module categories over it? And can you like bootstrap your theorem into some statement that fits into Ivan Losev's Fock space categorification stuff?
Yeah, I understand the question. I don't really have an answer. I mean, for me, I'm still not very good at this, what you call the cellular structure on the Heisenberg category. I'm kind of good at these cellular structures when you have finite dimensional categories. So I'll shut up now because I don't have an answer.
So I have another weight question. So this second part of the talk was starting with a quiver, which is of type A infinity or AN or something.
Yes.
So when I change the quiver here, can I define a corresponding Heisenberg?
When you
categorification?
you mean not to some non-type A quiver, right?
Exactly. So I want to change.
No, I don't know how to do that. Heisenberg is very much a type A object. It's built from essentially built from symmetric groups or degenerate affine Hecker algebras. So
but it's somehow double type A in the sense that KLR for me is already type A, but you can take any quiver. But the two
right,
math,
but yeah, but you know, you're going in the quiver direction, whereas
yeah,
Heisenberg,
I want to go
Heisenberg is the classical type A, not the quiver type A. You know, it's really this more classical object, and of course it acts on all those classical type A Abelian categories in representation theory. It doesn't see geometry of quiver varieties. That's sort of the non-classical type A in some way.
Maybe I can also ask, so in this, on this page, you have your eyes are elements of the image of integers in the ground field.
That's what you get in lots of those examples, like Rep GLN, yes.
But you can get other elements of the field.
Right. I mean, if you typically what happens is when you start defining some of these categories, your set I, this quiver starts to split into different components, that's kind of one of the nice things about Heisenberg is it acts. You can get it to act on categories that you can still deform.
But sorry, by quiver, you mean the Dynkin quiver?
I mean, for example, you could take a quantum group, for example, a parameter Q, and then you can deform so that Q becomes a root of unity. And when you do that, this spectrum will change. The Heisenberg acts kind of so naturally that you can still deform. But once you've got to the point that you've fixed your parameters, this spectrum is all the kind of discrete data. So once you've got your spectrum and passed to Cax-Moody, you can't deform anymore. I don't know if that made any sense, but.
So when I is not an image of an integer, you still have action of ENF.
Yeah.
And that still increases I.
Yeah, exactly.
By one or lower by one.
That's right. And I mean, these Deligne categories is another good example. These Deligne categories are semi-simple at non-integer parameters. And in that case, the spectrum will have two components. And when you deform so that the parameter in the Deligne category becomes an integer, this spectrum will sort of collapse to one component, and it'll start, instead of being semi-simple, it'll start being interesting, and you'll get Jordan blocks.
And so in the Deligne category case, your integer parameter k is 0.
Yes. Yeah, that's right. I mean, all these GLN examples somehow they're all central charge 0 cases, and they all give their Grothendieck groups all level 0 representations of Cax-Moody.
But you still have actions of you still have Categorified quantum group acting just at level 0.
Yes.
Categorified level 0.
Mm-hmm. And you know, that's, to me, that's sort of quite uncharted territory where I mean, I know everything about highest weight modules, I feel, but as soon as I'm in level 0, there's all these interesting irreducible representations that I'm a bit ignorant
saying that when I is not an integer, you don't get highest weight representations, you get categorifications of some other representations.
I mean, obviously, when you're in central charge 0, you're not categorifying highest weight anymore. You still get all these crystals appearing naturally out of categorifications. But to me, this theory of crystals in central charge 0 is a bit more, somehow it seems more a wider story.
And so I guess that's new thing. That's a new.
Well, I guess it's a new point of view, maybe, that says, look, you should tell me more about it. I mean, for me, kind of one of the universal module categories you see in this story are these lowest tensor highest weight categorifications. You know, we focused a lot on highest weight modules or lowest weight modules, but really, if you're doing affine Lie algebras, you should be thinking about lowest tensor highest weight modules. And understanding kind of canonical bases and crystal bases of those. And
so just when you say lowest tensor, highest weight module, so what do you mean?
So just take an integrable lowest weight module of some lowest weight, tensored an integrable highest weight module of some highest weight.
Right.
And you know, Lustig used these in his construction of canonical basis. When you're not in finite type, they become very important modules.
Mm-hmm. And you see amplification of them in the
they're asymptotically faithful, so you can see the whole of U of G from those. Whereas if you just restrict to highest weight modules, you miss a lot of the story. Not in finite type. Finite type's fine, right? But in affine type.
Thank you.
So can I ask about these crystals? You said you get these perfect crystals. So I never got
that's a different
feeling
use of the word
for this condition.
That's a different use of the word perfect. You get a perfect basis, which has nothing to do with a perfect crystal.
Oh, it's not a perfect crystal. Oh, okay.
No, it's a perfect basis. The word perfect is used for more than one thing.
Okay, then okay. I was confused. So then my question is gone.
John, can you say a word about how you proved that you get an integral representation of G?
Yeah, I think you know that argument. You get an integrable representation automatically. You have to show that EI acts nilpotently, but in fact, you have to.
It's just some cyclotomic.
Yeah, it's just some cyclotomic deal, and you just have to show that actually there's a dot acts nilpotently, and then use this expression for the usual idempotent projectors in the Nilhecker algebra. Okay.
More questions?
Well, I will again fix my typos and update the slides and send them to Nicole.
So we can post them.
Yeah.
Just more questions. Let's thank John for a remarkable talk. Thank you.
Okay, thank you, everyone.
Thanks, John.
Oh, I can't end the meeting. There we go.